Look closely. Can you guess who this person is? It feels familiar. The face, the posture, the aura. You've seen this person before, but where? After retrieving bits of information, your brain finally comes to an answer. But a computer can't rely on memories and intuition like we do. It only sees raw data, like numbers and pixels. So how can it possibly recognize a face or tell two faces apart? That's where convolutional neural networks come in. CNNs are a special type of neural network designed specifically to analyze images. The key behind a CNN is the convolutional layer. But what exactly is convolution? Put simply, convolution is a mathematical process where a small matrix called a filter slides over an image, looking at one patch of the image at a time. The filter is multiplied with the pixel values of the patch and then summed up to produce a single number. This value becomes a pixel in a special image called a feature map, where certain features like edges or textures are highlighted. But wait, how exactly does this filter move across the image? That's where stride comes in. A stride of 1 means the filter moves 1 pixel at a time. A larger stride skips more, reducing detail and the output size. Also, to avoid shrinking the image too much, we use padding, adding zeros around the border so even the edges get processed. After each convolutional layer, the network applies an activation function, most commonly the ReLU, or Rectified Linear Unit. This function introduces non-linearity, which helps the network learn more complex and varied features by transforming negative values to 0 and keeping positive values unchanged. To make computation more efficient, CNNs utilize max pooling layers after the convolutional layer. Pooling layers essentially pick out the maximum values from a smaller region within the feature map. Think of it like zooming out on a photo to get a quick summary. Instead of remembering every tiny detail, you focus on the brightest or most important spots in each section. Both convolutional layers and max pooling layers make up the bulk of the feature extraction phase of a CNN. Once relevant patterns have been found by the network, it goes on to the classification phase. In the classification phase, the data first must be flattened. This is because the fully connected layers expect a one-dimensional list of numbers. So the multi-dimensional data from the feature extraction phase must be reshaped or flattened into a single vector. Once flattened, this data passes through the fully connected layers, which act like a traditional neural network. These layers weigh and combine the extracted features to make the final prediction. At the very end, a special activation function, often the softmax, is applied to produce probabilities for each possible class, indicating how confident the model is for each prediction. Now that we know more about how CNNs work, let's build one using TensorFlow and Keras. We will build our model to tell the difference between a picture of Messi and Ronaldo using the dataset in the description below. Let's start by importing necessary libraries like so. Make sure you have both TensorFlow and Pandas installed. Using Keras, let's actually assemble our model. We start off with the convolutional layer, specifying our filter size and the size of the image with the input shape parameter. After every convolutional layer, there's a max pooling layer, and we can specify the size of the pooling matrix here. Let's repeat this process 3 times, increasing the neuron count by a multiple of 2 each time, so that the model can detect a range of low-level patterns, like edges, or high-level patterns, like facial structure. Once we're done with that, we can move on to the classification phase of our CNN. We first start off by flattening the data, and then creating a fully connected neural network using a dense layer. We also add a dropout layer to randomly drop 50% of the neurons in training. This forces our network to not rely too much on one specific feature, making it less prone to overfitting and more generalizable to new images. Our last layer has just 2 neurons to represent our 2 output choices and uses a softmax activation function. Now that our model is assembled, we can configure it for training using the compile method. We're essentially telling the model to be training to maximize accuracy. We can load in our data using the flow from directory method, which assumes our images are organized in folders named after each class. We will also resize all the images to be 256 by 256 pixels, splitting 20% for validation and loading them in batches of 32 with labels returning as integer. After training, we can make sure to save our model to a file so that we can load it later for making predictions without retraining. Nice! We have just created a convolutional neural network with a pretty decent accuracy.